college prep physics, looking at efficiency of work. And efficiency just says that that's the percent of energy that's not lost. And what does that mean? Well, all processes, because of friction, essentially, every single process that happens is inefficient. It loses energy. Not always friction, but friction is the guarantee that it'll always happen. But and so I'll just show you some examples. Like if you look at a light bulb here, say you take this, say you put 100 watts into both of these light bulbs. This is like what we call the high efficiency light bulb. Well, a high efficiency light bulb, you put 100 watts in, you only get 20 watts of light out of that. 80%, 80 watts of the light, of the energy that goes in, the power that goes in, is still lost to heat. You know how they're cooler? They're a lot cooler than these, is 95 watts is lost to heat. So light bulbs are extremely inefficient processes, even the high efficiency ones. Now, this is actually fairly old. It could be that there's ones that are more efficient than 20% now, but when I made this a few years ago, 20% was a high efficiency light bulb. Okay, so what I mean, so again, if you put 100 watts in, you get 20 watts of light, which is the useful stuff. That's why you use a light bulb. No one uses, I don't think, unless it's one of those Betty Crocker ovens, then you use a light for heat. But most of the time, you never use a light bulb for heat. You use it for light, and so that's what I mean by efficiency. It's only 20% efficient because of the energy you're putting in. Only 20% is useful to you. Okay, so we use the term useful energy. Okay, this is useful. This is wasted, unless you're using a Betty Crocker oven. But then it's a whole different story. Okay, so the energy then, the equation is percent efficiency is the useful energy out, and so that's like in the case of the high efficiency light bulb, it's like the 20 watts, that's the useful, over everything you put in, which in this case would be 100. Okay, so you put 100 in, there's my useful, and that's what you put into the formula times 100. So it's the useful energy divided by the input energy. Oh yeah, here's my example for the light bulb, right? So if I said my energy in was 100, my useful energy is 20, I calculate percent efficiency. Okay, so it's 20% efficient. That was the easy one, just 20 and 100. They're not always that easy. Here's the thing. So when we talk about useful energy, like for example, I was saying energy, but I was using watts, for example. I was kind of using them interchangeably, which theoretically isn't correct, but in the efficiency calculation, as long as you're talking power and power, or energy and energy, or work and work, the equation works for everything. And you'll see what I mean in a sec. So in this example, say you've got a crane and it lifts a mass of 2,000 some I-beam or some big heavy thing from the ground to a height of 45 meters. It takes 25 seconds. The crane motor has a power rating of 450 kilowatts. So here, this little piece of information right here, when you're given a power rating for a motor, and this is, I mean, in life, but in physics class specifically, in the question, this is like the input. This is what's saying what's going into the motor, 45 kilowatts, which is 45,000 watts. So the useful power for a crane or for anything else is the job it's intended to do. And a crane is intended to lift something. So by lift something, I'm saying that's MGH. That's the work. And then to get the power part, you just divide it by time. So that's really what I'm doing in this equation right here. I'm saying the useful work, the work I want the crane to do, is to lift up a 2,000 kilogram mass. So, and the power then is that divided by the time it takes to do it. So that's my useful power. Turns out to be 35,000 watts. The input power, so remember in these questions, if it says input power or power rating, that's the input. That's the bottom of the equation. Okay, the bottom of the fraction. So this particular crane in this example is 76% efficient. And I mean, and a crane's a great example of, well, where's the inefficiency? Well, certainly friction in the lifting device. But also there's, if the crane, this crane motor, probably that whole 45,000 watts might operate all the lights and all the seat warmers or whatever for the person working in it. That might be the total energy in, right? So there's lots more that a crane does besides just lifting things. It's just that its design, its useful work, it's the reason for its existence is to lift stuff, right? And so that's why that's the useful energy. Okay, my second and last example is Batman's motorcycle has a gasoline engine with a power rating, scientific notation, that's good for you to practice, that's 26,000 watts. The engine does, I think that's a huge typo, does 340,000 joules of work at full power in moving the motorcycle over a period of 85 seconds. Okay, so lots going on in that question, big numbers, right? So I know my input power. So remember, if you see power rating, that's your key that to yourself. You say, okay, she's talking about input there, okay? The engine does that much work when moving over that period of time. So when it says what it actually does, then that's the useful part. And that's the hardest part with these questions, is distinguishing. The other thing is that you're going to have one number on the top, you're going to have one number on the bottom. The bigger number has to be on the bottom, if in doubt, okay? But I was looking at my givens then, my input's the 26,000 watts, my useful work, and it's work, so now I'm talking power and work, two different things, right? My work, though, is the 340,000, or 3.4 times 10 to the 5, but I'm given a time. So I can turn this work into power by dividing by time. So when it asks me for power, then I just take the work, divide it by time, and I get the power. Okay? And the efficiency then is the useful power, the power output of the thing, divided by the input. And there you get, it's not very efficient. But again, you think the old motorcycle there, it's got lots to do. It's probably got seat warmers for them, and it's got to make lots of noises and lights, and all those things aren't included. When we're talking about this, we're probably talking about, you know, the work it does to actually move the motorcycle. Well, Batman's motorcycle does a lot more than just move things, obviously. So, you know, it's not going to be very efficient in that sense of the word. Okay? So, yeah, you have to practice these. You should definitely try to find some questions that I've assigned, because, you know, it is hard to sometimes know what I mean, which one works, right? And just reading the questions and seeing different examples is helpful. Okay, that's it for today.